Take the parabola y equals x squared. All coordinates here are real numbers. Slide it 3 units to the right. Every textbook says the new equation is y equals x minus 3 squared. Minus 3. You move the graph in the plus direction, and the formula answers back with a minus. You have probably memorized that. But try the next one and memory runs out. Spin the same parabola a quarter turn about the origin, 90 degrees anticlockwise. What is the equation of the curve you are now looking at? There is one rule that answers both questions, the shift and the spin. And once you have it, no transformed graph will surprise you again. Here is the whole idea of this episode, in one sentence. To find the equation of a transformed figure, take a point, pull it back to where it came from, and put that pulled back point into the original equation. Pull back, not push forward. You substitute the inverse transformation, not the transformation itself. That is the entire rule. The minus sign in x minus 3, the quarter turn, mirror images, zooming, every one of them is this single sentence, applied to a different way of moving points. The rest of the episode simply makes this sentence obvious, and then lets it run. First, what is a figure? A curve looks like a single object, but it is really a crowd, infinitely many points, one at every position along it. And what is an equation? A test. The equation y equals x squared does not draw anything. It answers yes or no. Feed it the point 2, 4. Is 4 equal to 2 squared? Yes, so the point is on the curve. Feed it 2, 5. No, off the curve. The parabola is simply the set of every point that passes the test. So when we transform a figure, we move each of its points, one by one, and the transformed figure is the crowd of landing positions. To describe it, we need a new test. Ask it directly. When does a point P belong to the new, transformed curve? Exactly when P is the landing position of some point of the old curve. Run the film backwards, undo the transformation, and P must land on the old curve. So the new test is, pull P back, then ask the old test. Now watch the minus sign appear. Shifting right by 3 sends x, y to x plus 3, y. Undoing it subtracts 3. So the new equation asks the old question of the point x minus 3, y, which gives y equals x minus 3 squared. The minus sign is not a convention. It is the undo written down. Now the quarter turn with the same rule. Rotating 90 degrees anticlockwise sends the point x, y to minus y, x. Undoing that is a quarter turn the other way. X, y goes back to y, minus x. Substitute the pulled back point into y equals x squared. Minus x equals y squared. That is the rotated parabola, opening to the left, exactly as the picture demands. Notice the trap. If you substitute the forward rotation instead, you get x equals y squared, a parabola opening to the right. It looks plausible, and it is the mirror image of the truth. As a check on the arithmetic, take points on the original, rotate them, and every one of them satisfies our equation, and none of them satisfies the trap. The derivation is the reason, the points are the audit. Now let the rule run. First, reflections. A reflection has a lovely property. Do it twice and you are home. Folding across the same mirror twice changes nothing. So a reflection is its own undo, and our rule becomes effortless, because pulling back is the same as pushing forward. Across the y-axis, x goes to minus x. So in the equation, replace x by minus x. Take y equals x squared minus 2x. Fold it across the y-axis. Y equals x squared plus 2x. The picture confirms it. The dip on the right becomes a dip on the left. The same move builds the whole table. X-axis, replace y by minus y. The origin, flip both signs. The diagonal line y equals x, swap x and y with each other. 4 mirrors, 1 rule, no memorizing. The table also works in reverse. You can read symmetry out of an equation before you have drawn anything. Look at x squared plus y squared, at most 2 times the absolute value of x, plus 2 times the absolute value of y. Replace x by minus x. The absolute value does not care. The equation is unchanged, so the figure equals its own reflection and must be symmetric about the y-axis. Same for the x-axis. So we only need the quarter where x and y are both non-negative. There the absolute values disappear and completing the square gives a disk. Center 1, 1, radius root 2. 1/4 is a disk. Fold it across both axes, and the whole figure blooms into a 4-petal flower. We drew 1/4 and got the rest for free. Second example, harder. The mirror itself is now slanted. Reflect the parabola y equals x squared across the line y equals x plus 1. None of our 4 mirrors is this line. But we can build the new mirror out of moves we already own. Slide the whole plane down 1. The mirror becomes y equals x. Fold across it, that swaps coordinates. Slide back up. Follow a point through the 3 steps. X, y drops to x, y minus 1, swaps to y minus 1, x, rises to y minus 1, x plus 1. So the slanted reflection sends x, y to y minus 1, x plus 1. And being a reflection, it is again its own undo check. Apply it twice and you return exactly to x, y. Complicated transformations are assembled from simple ones. That is a technique worth keeping. Now the image is one substitution away. The pullback of x, y is y minus 1, x plus 1. Put that into y equals x squared. X plus 1 equals y minus 1 squared. Rearranged, x equals y minus 1 squared minus 1. A parabola lying on its side, opening to the right, with its turning point at minus 1, 1, precisely where the turning point of the original lands under the mirror. One line of algebra did what the picture promised. Where do the parabola and its reflection cross? Substitute y equals x squared into the image. X plus 1 equals x squared minus 1 squared. Expand and collect. X to the 4th minus 2x squared minus x equals 0. It factors completely by hand. X times x plus 1 times x squared minus x minus 1. 4 real roots, 4 crossings. 0 and minus 1 give the points 0, 0 and minus 1, 1. And the mirror sends each of these to the other. They cross as a matched pair. The last factor, x squared minus x minus 1, is the equation of the golden ratio. Its 2 roots are points where the parabola meets the mirror line itself, points the fold cannot move, so both curves must pass through them. The golden ratio, sitting quietly in a reflection exercise. It was there the whole time. Last example. The transformation is now a zoom. Scaling from the origin by factor k sends x, y to k, x, ky. Undoing it divides. The pullback is x over k comma y over k. So a scaled figure's equation is the old one with x and y each divided by k. Try it on y equals x squared, with k equal to 1/2. Substituting 2x and 2y gives 2y equals 4x squared. That is, y equals 2x squared. So y equals 2x squared is not a new shape. It is y equals x squared at half zoom. In fact, every parabola is a zoomed copy of every other. They are all similar figures, in the precise geometric sense. For parabolas, perhaps you believe that already. The next one is the surprise. Claim the graph of y equals 4 to the x is similar to the graph of y equals 2 to the x. Not analogous, similar, as in same shape, different size. Shrink y equals 2 to the x by 1/2. By the rule, replace x and y by 2x and 2y. 2y equals 2 to the power 2x. Solve for y. Y equals 4 to the x divided by 2, which is 4 to the power x minus 1/2. But that is exactly the graph of 4 to the x, slid half a unit to the right. And a slide changes nothing about shape. So, shrink the 2 curve by half, nudge it half a step, and it lies exactly on the 4 curve. Watch it happen, the two graphs click together, point for point. The same argument works for any two bases. Every exponential curve ever drawn is the same shape at a different zoom. Steeper growth is not a different curve. It is the same curve, seen from closer in. One rule ran the whole episode. A figure is a set of points. Its equation is a membership test, and the transformed figure's equation is the old test, asked of the pulled back point. Always the inverse. Always the undo. Slides, quarter turns, 4 kinds of mirror. A slanted mirror built from 3 moves and zooms, 1 substitution each. How far does it reach? Exactly as far as the undo exists. A transformation that flattens the whole plane to a single point cannot be run backwards, and for it, the method says nothing. But every rigid motion, every reflection, every zoom, everything you would call a change of viewpoint, has an inverse, and surrenders its equation to the same one-line move. Harder versions exist. The source seminar reflects a parabola in a steeper mirror, where the crossings need quartic tools. The rule is unchanged. Only the arithmetic grows. So yx minus 3? Because the equation of a moved curve interrogates the point that came before the move. The minus sign is the undo, made visible. The rotated parabola, the 4-petal flower, the golden crossings in a slanted mirror, and the single shape behind every exponential curve. All of them fell out of that one sentence. Substitute the point you pulled back. To know where something is, ask where it has been.